we are going to discuss a very important theorem in group theory, that is cancellation law we have to prove. Okay, so let us take that now. Right, so if A, B, C are three elements in the group G, then AB equals AC implies B equals C. And this is called what? Lift cancellation law, because the left side of A we are cancelling, by that way we are getting this. And this, that is a BA equals CA, we can cancel left hand side, or sorry, right hand side, and we'll get this one. Am I correct? So this is called the right hand side cancellation, and this is called the left hand side cancellation. Okay. So in the group theory, we have to remember all the properties of the group. That is very, very important. Okay. All the properties of the group, we know that a closure property, then inverse property, and identity existence property. All these properties we must understand before entering into proving this type of problems in mathematics. Okay. Now let us prove that now. AB equals AC implies B equals C. Let us prove this now. Then afterwards, we will be proving the next one. Okay. Now let us prove that. Now I go for ink. White ink is the better, or I can take the blue ink. That's better, I think so. Okay. Right. Now let us prove this first. That is, AB equals AC implies B equals C. That's what we will prove now. And afterwards, we will prove the second part. Okay. Right. So this is what we call a cancellation law. Cancellation law. We are proving now. Okay. Now let us prove that now. Yes. Now we'll prove now. Proof. Now what I am doing there, we cannot accept this fact. We have to prove this. Okay. So given, you can say that it is a given that what is given to us is that AB is equal to AC. For any ABC belongs to G. This is given to us. Okay. Right. Now what we have to prove? What we have to prove that is B equals C. That's what we have to prove. Okay. That's what we will do now. Okay. So if AB equals AC, then we have to prove that B equals C. That's what we have to prove. Okay. Right. Now, let us take this now. Let I'm taking like B. I'm taking 1. Okay. Right. B, how can we write? Okay. B, I can write it as B into identity element. Why? Because we know from the property that if an identity element is operated on any element of a group, then we will get the same element. That's what we know already. Am I correct? Therefore, in the place of B, I can write it as BE. Okay, right. Now this BE, I can write it as, instead of this the identity element, I can replace by B into A inverse into A. I can, because from the property of from the group property, we know that for any element, okay, suppose that an element belongs to G, then its element and its inverse element operated on by the binary operation, definitely we will get an identity element. Am I correct? That is what the group theory says. So what I have done here is that I have, instead of the identity element, I have written A inverse into A. Okay. Now what I can do here, so this is exactly equal to or we can write it as A inverse A A inverse A. So now this from the property we can associate these two elements. So from the associative law we can write it as A inverse into AB. I can write from the associative law because the group satisfies the associative property. We can associate three elements as we like, but the final result is same. That's what we know that. Am I correct? So the associative property says that we can associate any three elements in a group in any way we want, but the resulting element doesn't change. That's what the group theory says. Okay, right? That way I am associating and I am getting this. I have associated in different way here. Now this equals AB, but we have assumed already that AB is equal to BC. AB is equal to BC. That's what we have assumed already. So this I can substitute here to get a new structure as A inverse into AC. A inverse into AC. Why? Because 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 we have assumed that AB is equal to AC. We have assumed already. So in the place of AB, we can replace by AC. That's what we are seeing here. Now, next step is that, okay, we have substituted instead of AB is equal to AC. Now, again, I'm associating in different way. That is A inverse into A inverse into A into C, because associative property is valid in any group. Associative property is valid in any group. So we can associate any way that we want. So I have associated A inverse and A, then afterwards B. Okay, afterwards C I can associate. But we know already that any element with its inverse, any element which is inverse will give us an identity element. Any element in a group, when it is associated with the inverse of it by the binary operation, we will get the identity element. That's what the theory says. So what I am doing there, instead of this, I can substitute this. This C is as it is. So by the rule again, we know that if C is any one element belongs to G, and if E is the identity, when any element is associated with the identity, we will get the same element. Okay, so any element is associated with the identity element, we will get the same element. Okay, that's what we know well from the group theory. So we have that and this element is associated with the binary operation defined there on E. What we'll get is that is equal to C. So now what we see here, this is exactly equal to B. Am I correct? So B equals this, B equals this, and B equals this, and B equals this. So B equals C. That's what we have to understand. Okay. So the similar way we can prove this the right cancellation also. So what we have proved is the lift cancellation law. The right cancellation also we can prove this way. So lift cancellation law is proved and the right cancellation law can also be proved by the way that we have proved just before. So with that I come to the end of this class. The next class we will be discussing with the other theorem. Okay, so thank you very much indeed for your presence here. Okay, thank you.